Let's keep down this probability road. This is a really short lesson. We're going to talk about and events. So notice I'm talking about plural events, like multiple different events happening. Like I'm going to flip a coin not once, but multiple times. For example, I'm going to just revert back for a moment so that I can clarify, because we have seen an and before, but that was a single event. So I'm just going to scroll to the bottom of the 7.6a. So notice right down here, when I asked you, what is the probability? I'm looking right down here. What is the probability that a randomly selected student was a girl and chose pizza? This is one event, right? So that one meant I was looking for the overlap. So girl and chose pizza was the 16 out of the 95 students. There was one probability being asked for here. So and with a single event, that was looking for the overlap. If we're talking about in today's lesson and events, plural, that means that there's multiple events happening. So it's really worth talking about the fact that we have to know what it means to be independent events, right? And that means when the outcome of one event does not affect the outcome of another event, right? So they are not based on one another. And if that is the case, if they're independent, right, where the one does not rely on the other, then we can multiply their probabilities. That's all this formula is saying here, right? So the probability of the first event times the probability of the second. So here's a great example that's pretty easy to talk through that maybe highlights what we're talking about here by multiple events. So looking at our first one here, what's the probability of flipping a head on a penny 3 flips in a row? So, okay, event 1, well, on a penny, right, we either can get a head or a tail. So if I'm going to flip a head, that is 1 out of 2 options. So this is for the first flip, event 1, or flip number 1. Now, if I take that penny back out, the penny does not know if I got a head or a tail on the first flip. So we would say that these events are independent of each other. I am equally likely to get a head or a tail on the next flip. So to get another head would be, again, a 1 out of a 2 chance. So this is event 2. And likewise for flipping it 3 times in a row, still independent events. So this would be the third event. And because they're independent, we can just simply multiply these probabilities together. So if we multiply across, this becomes 1/8. So 1 out of 8 times, I would expect to get a head, 3 flips of a coin. All right, let's talk about one more example. And you might remember this one. I took this right out of our probability unit from Algebra 2. Imagine that I open up my desk drawer and I have certain couple of paper clips. I got 3 red ones, 4 green ones, 5 blue ones. So all together, we have 12 paper clips. If I take a clip from the drawer and then I replace it, and then I grab another clip, notice this is, again, 2 events, right? And if I replace the first clip, like maybe I bound the papers, handed them out, and then I put the paper clip back, I still would have 12 clips in the drawer. So we would say, as long as it's being replaced, that they are independent events. So what is the probability that the first paper clip is red? Let's talk about part A here. The first paper clip is red. So what we're really asking here for is probability of a red, and then the second one is a blue, if they get replaced. So the probability of getting a red paper clip, so imagine opening my drawer, I have 3 red ones out of 12 total paper clips. Then I go back and I put the red one away. And then what's the chance that when I go back for another paper clip later in the day, I grab a blue one? Well, there are 5 blue ones. And since I put the first one back, I still have 12 clips in the drawer. And so we literally can now multiply these probabilities. They are independent events. It's probably easier to multiply if we just reduce the first fraction to 1/4 and then multiply across. So 5 out of 48 here. Okay, so what changes a little bit is in part B and part C. What if I take that first paper clip out of the drawer and then I don't replace it? So I'm going to just emphasize this right here. And then I don't replace it. What is the probability that the first clip is red and the second clip is blue if it's not replaced? Like it still is binding paper. So I'm down 1 paper clip in the drawer. So now we're talking about probability of red and then blue, but without replacing that clip. So it looks like these are identical problems, but there is a key change here. So again, going for my first paper clip, what's the probability of getting a red one? It would be 3 out of 12. But if I've now taken that clip out of the drawer, I no longer have 12 clips in the drawer, I have 11 clips in the drawer. So what's the chance that I'm going to go back and get a blue one? Well, I still have 5 blue clips, so it'd be 5 out of 11. So notice how this changes from up above. They're nearly the same, but slightly different, right? Because we've got to account for the fact that they're not really independent events. This second draw depended on the fact that I took one from the first one. But we sort of create independent events by just adjusting the denominator. So again, to make the multiplication easier, let's reduce the first fraction. So 1 times 5, that gives us 5 over 44. So the probabilities are slightly changed here. Let's do part C, and then we're all set here. So what's the probability that I would draw a green, not replace it, and then draw another green paper clip from the drawer? So this time we're looking at, there are 4 green paper clips out of the 12 clips in the drawer. And if I've taken a green clip out and not replaced it, I'm now down to 11 clips, similar to the last example, but I'm also down 1 green paper clip. So I no longer have 4 green clips to choose from, I have 3. So to make this multiplication easier, we'd reduce that first fraction to 1/3, and then multiply across. This is 3 over 33, which reduces again to 1/11.